Hello, Chemistry 127 students. This is video number 1 for fall quarter 2016. So before I start, I wanted to get into why I decided to make videos. One reason is that there's less note-taking during lecture. Lecture doesn't become a race to write down everything on the slides. Now you can take notes at your own pace and then bring your notes into class. Then our class time can be used for some of the more difficult but also more fun things like applications of these topics, the different activities and labs we're going to do, and also group work. So let's start with our first topic today, isotopes. So on a periodic table, I just picked a sample element to talk about for isotopes, and that is magnesium. Pull up my drawing aid. So go ahead and pull out your own periodic table that you got on the first day of class, or pull one up online. It has two numbers associated with magnesium. One of them is 12. And you probably remember that this is the atomic number. And it is the number of protons. So all magnesium atoms will have 12 protons total. The other number associated with magnesium on the periodic table is this 24.31. So this is a value called the average atomic mass. And it's in a unit that is called AMU, and atomic mass units, right here. So I picked magnesium because its AMU, its average atomic mass, is actually not a whole number. It's not really close to a whole number. It's not close to 24.00. It's not close to 25.00. It's within a mixture, which is because there are different isotopes of magnesium, and they vary in the number of neutrons that they have in the nucleus. Number of protons, of course, is unchanged, but we can have different magnesium numbers with different numbers of neutrons. So all of these isotopes are then pulled together for a weighted average, which creates the average atomic mass. So for magnesium, it has 12 for its number of protons in the atomic symbol. For one possible isotope of magnesium, the mass number could be 24. So here's the mass number. And this is the number of protons plus the number of neutrons. So everything in the nucleus. We got 12 protons, and in this case, we'll have 12 neutrons in this particular isotope. Magnesium has a couple more isotopes, though. One of them is magnesium 25. So its mass number is 25, still protons plus neutrons. We'll always have 12 protons, although here we're going to have 13 neutrons in this particular magnesium atom. Then the other common isotope for magnesium is just called magnesium 26. We don't always have to write the atomic number here in the atomic symbol, because if we have the magnesium part, we already know it has 12 protons. So again, the mass number is the protons plus neutrons. And in this case, this magnesium atom would have 14 neutrons. So these three isotopes are then used to determine the average atomic mass, which is a weighted average based on the abundance of these three isotopes here. So the average atomic mass depends on all of the isotopes present, the number of isotopes. Magnesium had 3, so I have 3 here in my example, but it could be 2 or more. We need to know the mass of those isotopes and their abundance. We usually kind of give the abundances in a percent, but then we need a decimal number, convert that percent into a decimal for the formula. So how we would do this, or how we could otherwise symbolize this, is to use sigma, which means sum. The abundance in a decimal form times the mass of that particular isotope, and then this product would then be added for each of the different possible isotopes. So let's do a practice problem here. We've got silver, Ag is silver. So if you have some silver jewelry at home, it's composed of these two different isotopes. So we have the masses of each isotope in AMU and then their abundances. So we can use this to determine the average atomic mass. We'll start with the first isotope here. So you can see that the mass number in the atomic symbol is 107, but then the AMU is 106.9, it's just shy of 107. So in the atomic symbols here, based on the number of protons and neutrons. But each proton and neutron isn't exactly one AMU. So we get some number of AMU that's just slightly away from the actual number of protons and neutrons. So this information, the AMUs, will actually be provided. So here we have the actual mass, 106. And then multiplied by its abundance in a decimal form. So in this case, 0.5184. Then we're going to add that to the information for the other isotope. This has a mass of 108, 90476, times its abundance in a decimal form, 0.4816. So if you do those piecemeal, the first term comes out to be 55 and some change. Second term comes out to be 52 and some change. And then we'll want our answer to be in 4 sig figs for this question, so I'll round to that. So 107.9 AMU for this particular isotope is the average atomic mass. Okay. So for just any atom in particular, the number on the periodic table is in AMU. So if we had one particular atom of magnesium, it would weigh on average 24.31 atomic mass units. But we don't usually have just one atom of something, we usually have many, many atoms of something. And we use a specific number of those types of atoms. And that unit for just a huge number of atoms is called a mole. So think about maybe buying a dozen eggs at the grocery store. You don't need to pick out exactly 12. You can buy just a carton that has a dozen in them. And we use something like that for atoms. This is the mole. And the actual mole is 6.022 times 10 to the 23rd items inside 1 mole. And why did they pick this number? Well, a scientist, Avogadro, actually decided that it would be carbon 12, so isotopes of carbon that have a mass of 12. And how many atoms of that carbon 12 you would need to get to exactly 12 grams in weight. So this is the number of atoms that we came up with. And so that's what we define as a mole. So here I put items per mole. So this could be something like atoms. Like up here, if we had 1 mole of magnesium, the mass of all those magnesium atoms would be 24.31 grams. We could also have something like molecules. If you had 1 mole of glucose molecules, then that mole of glucose molecules would contains 6.022 times 10 to the 23rd molecules inside it. You could also have a mole of maybe something like grains of sand or skateboards or whatever you want. But in this class, we'll talk about atoms, molecules. We'll probably talk about moles of photons and also moles of electrons too. So usually atoms and molecules. So for the mole, we actually use this quite a bit to actually convert between moles and some other things. So mole. And the first way we could use this is to convert to grams, or to convert between moles and grams. So just like if we were converting between maybe feet and centimeters, we would need a conversion factor to be able to do that. We have one between moles and grams, and that is called the molar mass. That allows us to convert between grams and moles. So basically, it is however many grams per 1 mole. So just a very simple problem here. Simple example. We have 5 moles of something. We can determine what the weight of 1 mole is in grams. And I'll just use X grams for something. So in this way, we would cancel out moles to get an answer in grams. Then we'll do something kind of the reverse of that. Let's say that we had 5 grams of something. And then we want to determine how many moles that is. 1 mole would be X number of grams. So in this way, we would cancel out grams to get an answer in moles. So this is how we can convert between moles and grams with this kind of conversion factor, grams per 1 mole. We also know that moles contain numbers of items. So we can convert between a number of moles and then the number of items there. And the conversion factor to do that is Avogadro's number. So I'm going to just abbreviate this N. So between moles and number of items, let's say again that we have 5 moles of something. We know that in 1 mole, we have 6.022 times 10 to the 23rd items. So in this way, we can take a number of moles and then convert that into a number of items. And we can go the opposite way as well. So I'll just pick a number, 5 times 10 to the 24th items. We can again use Avogadro's number to convert into moles. So we want items to cancel out. So in this way, these 3 different measurement forms, grams, moles, and actual number of items, number of atoms or molecules, we can use conversion factors to get from one to the other to the other. And these conversion factors, the first one that we learned about is Avogadro's number, N. So this is something that if you've got your periodic table handy or your equation sheet, you'll see that it's on there, 6.022 times 10 to the 23rd. You might memorize it by the end of the quarter, but it'll always be there on a quiz or exam on your equation sheet. The other conversion factor we use between moles and grams, the molar mass, or grams per mole, is something that is very specific to the type of thing that we're actually converting between moles and grams. But the molar mass is something that you can always find out from something called the chemical formula. So you've seen chemical formulas before, even if you didn't know quite what they were called. So here's a very simple one. H2O is a chemical formula. We can also have something like maybe AlCl3, another chemical formula. So in this one, there's 3 chlorine atoms for every 1 atom of aluminum. So that's a kind of like a ratio of the different types of atoms and how much are put there. So this kind of chemical formula and molar mass is something that we will use. So sometimes this is called molar mass. Sometimes I might call it molecular weight because that's what we usually talk about for biological molecules like proteins or the blue dye. Sometimes it's called formula weight, especially for ionic compounds like NaCl. And sometimes we would just write grams per mole. So those are ways that all refer to the same thing, and I might use them interchangeably. I might use molar mass more if I can remember to do that. So just a few examples of how to determine this. So molar mass, first of H2O. So we need a periodic table to be able to do this. Go ahead and pull yours out. But we also need the chemical formula. So here we have 2 hydrogens. So we'll use its weight on the periodic table. And then add that to the number of oxygens. There's just 1, and it weighs 16 grams per mole. So here we get a total mass of 18.02 grams per mole. So this is our conversion factor between grams and moles for water, for H2O only. Every molecule has its own conversion factor, its own molar mass. For some other molecule, I picked another chemical formula here, more complex. We have 2 scandium atoms, and then this whole group is a sulfate, SO4, and that is present, there's 3 of them present for every 2 scandium atoms. So let's go ahead and find Sc on your periodic table. We've got 2 of those, and its weight is 44.96. Then we've got the sulfur, and we have the oxygen. We actually have 4 oxygen atoms. So here, this is the sulfur, and here's the 4 oxygen atoms. So this whole bit, the SO4, is then duplicated or replicated 3 times. So different color here. It's actually together times 3, all of this. We have 3 of these sulfate groups and then 2 of the scandium atoms. So when you plug this all into your calculator and then adjust for, there's no real significant figure issues here. So 378.13 grams per mole. So 1 mole of this particular compound would contain 378.13 grams. So this would be our conversion factor for this particular compound. So we can use these molar masses to then go through different types of things to find the different units present. So here's another example. We have K2CO3, this is potassium carbonate, and we happen to have 5.78 kilograms of it. We just need to convert that into moles. So we have, instead of grams, we have kilograms, but it's still a unit of measurement in mass. So we'll first need to convert from kilograms into grams. We know that kilograms is just a SI unit prefix, and you guys can take note of all of those. Then from grams, we can go into moles using our grams per mole information. So first we need the grams per mole of potassium carbonate, K2CO3, and I already have it here. (138.21 grams per mole. So we're starting out with our 5.78 kilograms. Now we need to convert that into grams for our conversion factor. Our grams per mole is in grams. So 1 kilogram, 10 to the third grams. And now we can use our grams per mole. To then determine the number of moles. And we want 3 sig figs for this particular problem. So we have 41.8 moles K2 CO3 total. Okay, now we have another compound, C2H6. We're given moles, so we need to find the mass in grams of that. We don't have any specific value. It doesn't need to be in any particular, like grams, kilograms, micrograms, anything. So we can just use plain grams. It makes it a little easier. And then we want to find the number of hydrogen atoms. So we'll need to go from moles, first of all, to grams. We'll do that using just the molecular weight. And we also need to go from moles to then the number of atoms. Okay, let's start with the first one. 10.2 moles. So to convert between moles and grams, we'll need the conversion factor, the molar mass, which I won't go through the steps to calculate this one here. It ends up being 30.08 grams per 1 mole for C2H6. And then here we do have 3 sig figs, so we'll keep it at 3 sig figs in our answer. 307 grams of the molecule. So what we need to do next is to find number of atoms. If you want to make it a little more challenging, you can take this number of grams and convert that back to moles and then to number of atoms. I'm just going to start with the 10.2 moles. So that's 10.2 moles of our whole compound, C2H6. So what we want to get finally is the number of hydrogen atoms. But right now we're starting out with a certain amount of our whole compound. So we need to get from, first of all, the whole compound to just moles of hydrogen. And we can do that using the chemical formula. So 1 mole of C2H6, we know from the chemical formula, would have 6 moles of hydrogen. Now that we're moles of C2H6 is canceled out and our units are now in moles of hydrogen. And we can use Avogadro's number to then convert between moles to the number of hydrogen atoms. So we end up getting, and again, 3 sig figs, 3.69 times 10 to the 25th hydrogen atoms. There. Okay, so this is just converting between grams, moles, and then number of hydrogen atoms, number of items per mole. There's one other thing we can do with this amount of moles that we have discovered as kind of a mediating factor between converting with things. So sometimes we don't have solids, we have a liquid solution. And very commonly in this class and many other classes, we'll work with an aqueous solution where something is dissolved in water. One example of that could be sugar water. We have, it's supposed to be sugar water, but it says iced tea. That would make an aqueous solution. Iced tea, I guess, is also an aqueous solution. So when we have an aqueous solution, like sugar dissolved in water, then the molecule that's present in the background that has the most number of molecules present is the solvent molecule. So I'm going to say higher number of molecules. And the thing that's dissolved in it is called the solute, and that's the molecule of interest, and there won't be as many of those numbers of molecules. And that's what we're interested in. How much solute is there present in some kind of solution? And we talk about concentration with this. And we have a certain unit for concentration called molarity, and it is symbolized with this capital M, and that is moles of solute per liter of solution. So just as an example, let's say we have something that is 0.5 molar. Its molarity is 0.5. That means that there are 0.5 moles of solute per liter. So for molarity, it's a unit of measurement like grams or like liters or moles. So we can actually give a SI unit prefix to this. So we could have something like, let's say 52 micromolar. So we have the micro in it there. That means that there are 52 micromoles per liter. Micromoles of the solute per liter of solution. So we can have things like I said, micromolar, millimolar. If you wanted to go wild, you could have something like maybe kilomolar or something like that. So now that we know a little about moles, we can determine how many are in a certain solution and what the concentration is. So first of all, to get used to molarity, we have a thing where we're given some amount of moles and a certain amount of liters. We want to determine the molarity M, which is moles over liters. So this one couldn't be simpler. 0.444 moles and 0.654 liters. And 3 sig figs, that ends up giving us 0.679 molar. And our solution, our solute is CoCl2, cobalt chloride. Then this next one is a little more involved. So here we're asking for molarity, but in millimolar instead of just molar, moles per liter. So we're going to need not just moles, but millimoles here in the numerator. Then instead of some amount of moles of a solute, we're given grams of that solute. Okay, so we have grams of solute. And we know that we want to get into moles of the solute and then millimoles for the numerator. The denominator is just going to be liters, so 0.5 liters. So we have, in this case, 0.515 grams H2SO4, our solute for this particular solution. So to convert from grams to moles, we'll need the molar mass of that. And for this one, I've already determined that. Actually, I'm just going to go ahead and write it here. 98.09 grams per 1 mole. So that would get us into moles. What we're going to need, though, is millimoles. So 10 to the minus 3 moles is 1 millimole. And I'm running out of space, so I might go ahead and write it way up here. I might actually erase these things. Right there. Yeah. Okay, so that ends up getting us this. Oh, need to erase that. 5.25 millimoles of our solute H2SO4. So going up there. So we know we have that many millimoles of our solute H2SO4 in a certain amount of solution, so 0.5 liters. So then we can do this to give us the actual millimoles per liter, which ends up being 10.5 millimolar H2SO4. Okay, so this is the end of video 1. It covered molarity and moles, grams, Avogadro's number, and also isotopes. So thank you for watching. See you in class.